This is the 22nd video in a course on single agent search. And in this video, we're going to be looking at heuristics, and we'll be starting to look at the question of where do heuristics come from, or what are different ways that we can build heuristics. And in this video, we're going to be doing an introduction to some ideas there. It's going to get us to certain types of abstraction or methods that we can use that work and don't work. And then there's a second video corresponding to this, which is now starting to look at how we can build heuristics using this. And this is going to give us our pattern database heuristic techniques. So we're going to start looking here. And if we just think about heuristics, so remember, a heuristic is a numerical estimate of the distance to reach the goal. And we can think about state spaces like the sliding tile puzzle. Actually, so let's just say we're working on heuristics. Okay, so we can think about like the sliding tile puzzle. And in the sliding tile puzzle, the default heuristic we typically use here is Manhattan distance. And this is it's actually Manhattan distance for every tile added together. So if I have, let's just do a very simple state space here. Okay, so I know in this puzzle here, I know where each tile is. I know where each tile is supposed to be, and I simply add up the difference between those two things of where it is versus where it's supposed to be, and that's going to give me my heuristic. And notice that I actually only do this for tiles. I don't do it for the blank. So I could look here and say, well, the 1 is sitting right here, and it's supposed to be here, so it is off by 1, 2, 3 moves. And so that would give me a heuristic of 3. And then I can say, look at the 2 tile. And so the 2 is here. The 2 is supposed to be here, so it's only off by 1. If I look at the 3 is here. The 3 is supposed to be here, so it is off by 1. And the 4 is right here. They're supposed to be here. It's here. The 4 is off by 1. If I continue here, so the 5 is supposed to be here, it's actually here, so it's off by 1. The 6 is here, it's supposed to be here, so it's off by 2. The 7 is here, and or it's supposed to be here, but it's actually here, so it's off by 1. And the 8 we see is sitting right here, it's supposed to be here, so it's off by actually 1, 2, 3. So if we did Manhattan distance here, we'd get 6, 7, 8, 9, 10, 11, 12, 13. It would say it's going to take a minimum of 13 moves. Okay, so that's something like that. And we've talked a little bit before that if we looked at what's going on here, we could think about, for instance, relaxing operators in our original state space. And there's an abstraction that says normally I can only move a piece into a new location if the blank is there. But we could think about, well, I might just be allowed to, independently move the 4. Let's just say I could move it from this location to this location. And if in my operators, I think about, well, if I don't allow, normally I don't allow a tile to move unless it switches with a blank. Maybe if I just allow any tile to move to any location, and then we could allow multiple tiles to be in a location or something like this, although it's not physically possible, it's logically possible, then there's abstractions like that that would lead to giving us something like Manhattan distance. And so that seems like maybe we could just do some abstractions like that. But we'll take a look at that and see maybe some ways that doesn't work out today, and that's going to guide us to understanding how it will work out. If we think about a grid map, so in a grid map, we have some sort of map here, and then we're going to have some sort of obstacles. I'll just draw them in green. So you could imagine, there's these obstacles that I can't get around, and I've got to find a path through this world that it is able to avoid maybe all these obstacles that are sitting here. So an actual shortest path, might come around here. It would actually hug the obstacles a little bit more closely. But what we're doing is we're thinking about abstracting this problem away. We're saying, well, if there were no obstacles in the world, then we'd be able to travel straight from the start to the goal. And so that abstraction of ignoring the obstacles, which again, we could think about. Normally, I can only move into a location if that location is not occupied. If we just remove that constraint, then I could say, well, I'm able to move into a location because, it's just another location that exists in the world. Then solving that problem would give me a heuristic where it would say, look, well, I just have to think about what would I do? I'd just be able to walk straight from the start to the goal, and I'd be fine. I'd be able to get my path there. Okay, so the question is, can we do something like this, where we want to take a state space, and the idea is, I have this state space, and I'm going to basically build an abstract problem, and my abstract problem is going to be exactly the same problem, or something like the exact same problem we had before. Oh, sorry, except I'm going to have no obstacles in it. Okay. And then I have my real problem that I'm really trying to solve. And the idea is that I want to go up here or the theoretical idea is that, okay, this is my start. I'm going to go up here and I'm going to solve this problem by doing some search up here to get to the goal. I'm going to do it in a abstract state space, so somehow as a simpler state space. And then in this process, I'm going to get some information that would allow me to then go in this original state space here. So this is one where I do have the obstacles. And in this state space, basically, I could go up into some abstract state space and use the information that is inside this search to guide me, so now I can actually more effectively search to the goal. So this is the idea, is we want to think about, can I build an abstract state space? Can I go into that abstract state space and do some computation that will give me a heuristic, which I'll then be able to use that heuristic when I solve my actual problem. And we are going to look at two examples here. I've done these ahead of time just to illustrate some things that can happen when we do that. The first one we're going to look at the top is the sliding tile puzzle. And the second one we're going to look at the bottom is Towers of Hanoi. This is just a 3-peg Towers of Hanoi with 2 discs, because we can draw this in a very small way. And so if we go back to the sliding tile puzzle, so I'll need a little bit more space down here to go back to the sliding tile puzzle. What we can think about is normally we have preconditions in order to apply an operator. So if I think, and this is looking a little bit at the planning definition. So this is looking at what would be STRIPS as a Stanford Research Institute problem solver. Today, this is PDDL, which is a problem description language. And and there's multiple versions of PDDL that give us quite a broad range of different parameters on what we can encode in our domains, the properties that they're allowed to have. So this isn't a planning course. I'm really not going to talk about PDDL at all, but I'm going to talk just a little bit about the operators that do exist in something like STRIPS or PDDL. And the idea that you have here is that when I want to apply an operator, so if I have an operator that says, for instance, move, and I want to move something from A to B, I'm going to have some preconditions. So the preconditions might be that now, there's a lot of different ways you can write this, and it depends on like how you're encoding your state space. So A and B are variables. We could say, for instance, if I want to do that, so these be preconditions, it has to be a precondition that B is blank, is the blank. So I can only move between A and B if B is blank. And if I assume there's only one blank, then I don't have to check to say that A is blank, because I just know that it will be. And then I might say that A is not equal to B. But I'm also, for instance, here going to say, so B is blank, and then adjacent A, B. Okay, so this says I can move things. If they're adjacent, then this automatically gives me the fact that they're not exactly the same thing, because two things that are the same location won't both be adjacent. Okay, so this gives me an idea of moving. I would say my precondition is that some location B has to be blank and A and B have to be adjacent to each other. And then I'd have some other conditions that says what happens. Well, after I do it, then A becomes blank and B gets the value of whatever A is. So I might have something here like is tile A. Just depending on how you're encoding it, there's a lot of ways you can do this. Okay, and so one of the ways that we can get into one of these abstract state spaces. So as I drew here, it's a little bit easier to show it in the grid map, but here I have my original state space and I want to apply an abstraction, which essentially allows me to get into a simpler space to solve. And of course, I hope that I can get an admissible heuristic from the simpler space, but then I want to be able to use the distances in the simpler space as heuristics for searching in the actual state space. And so just as an example of something we might do here, or that we could do, is we could come into here and we could say, look, I'm going to remove this precondition here that B has to be blank. And what this precondition is going to do, it was doing right here, well, it's saying, look, only when one tile is a blank can you move the tiles between each other. And so if we go up to our state space here, now this is a really small 2x2 sliding tile puzzle. It's actually a really uninteresting space because all you can do is go around in circles, right? Because you can't ever do more than swapping tiles. And so what we're going to talk about here makes a little bit more sense in a larger puzzle, but I'm just going to illustrate it here, and it's actually going to break down entirely. So I'm going to show you what can happen if we do something like this, and there's sort of two things that can happen. So in this case, what I actually see here, if I remove this condition that one has to be blank, then what this would allow me to do is it would allow me to take, for instance, if I were looking right here, maybe I'd be able to take this tile 2 and the tile 1 and it'd be able to swap them. And this would get me to a new state, which was 0, 1, 3, 2. And actually, I'm going to write this again. I just want to do it in a different color to make it clear what's going on here. So this is, as I said, 0, 1, 3, 2. And this would be a state that we could reach if we did this relaxation from this state right here, because now we'd be able to swap any two arbitrary tiles. And generally speaking, if you looked here, there'd be a lot of states that we could reach that would be actually new states. And so this is actually something that's really key. If I look at all the states that are here that are reachable in the state space, what I see is there are states that are unreachable, like this one. I don't have this written down anywhere here. And this comes from the fact that in the sliding tile puzzle, there's always two sets of, well, not always. If you only have one blank and some other conditions, there's always two sets of states that are unreachable from each other. So here, when I try to make a new state space or an abstract state space by relaxing my operators, then what happens here is I actually create a state that didn't exist or wasn't reachable in my original state space, but is reachable here. And now I'm actually going to grow the size of the state space. So that could be problematic. But if I do this right, what we should be able to see, what I can do, however, if I apply a second operator, I will be able to get back to a state that is reachable again. And so let's just look here. Where do I have 0, 1? Right. So what I do have is another edge right here. Because what I could do now, so I can have one action that I apply here by swapping these two. I can have another action that I get by swapping these two. And that is actually what takes me to this state right here. So what I've done here is I've added both edges and new states to my original reachable state space by removing the preconditions on one of these operators. Okay. And so what I see here is the state space in some sense is simpler because I can reach from this state to the goal state in 2 steps where previously it took 1, 2, 3, 4. So that looks like a simpler state space. However, I've been put in these spurious states that I don't actually want to reach. Okay. So we do have to be a little bit careful. It's pretty easy to avoid this in practice if we're engineering it ourselves. And there's been a little bit of work that's looked at how this can be done or looked at this process by Rob Holte, who's looked at just tons and tons of different abstractions and what happens there. Okay, so this is, there's 2 things going on here. One is that essentially there's this whole sort of shadow space. And we can just imagine that there's all these states here which were part of the overall possible state space, but they were never connected by edges. And so if I were to build a heuristic, I would have never seen them. And now they were connected together And now these edges, these states are all getting edges inside here. Okay, so that's a little bit of a funny example. And so I just wanted to show a second example where that's not going to happen. And this is the three peg towers of Hanoi problem. So typically this would be the start state here where I have two disks. I need to get these two disks to the goal state, which is over here on the third peg. And the normal conditions here that you'd have is that the smaller disk can only be on the larger disk cannot be on the smaller disk, and you can only move a disk when there's nothing on top of it. And so if we look at the state space then, and there's actually very, very interesting structure that you get, this recursive structure, no matter the number of pegs that you have or the number of disks, you get this sort of recursive structure in here. And so what I've done, this set of states all have the blue disk on the left, these all have the blue disk on the right, these all have the blue disk in the middle. And if we look here, then we could think about in a similar way that we thought about for the sliding tile puzzle, so I won't write this down, but we could be thinking about encoding our operators, and we'd ask the question, what happens if I say that, for instance, you can move a disk even if there's another disk on top of it? So we could imagine that I could just sort of arbitrarily move disks around each other. And, that seems like it's a pretty good abstraction. And actually the heuristic that it'll give you is it'll give you the number of disks that are out of place. And so we can look down here in the state space and we can ask, well, what happens when I change my state space in that way? And so for instance, what we would see from this state right here, I could, for instance, move the blue disk, something I normally wouldn't be able to do, either to the second peg or to the third peg. And in both of these cases, I would leave the red disk on the first peg. And so what that's doing is we'll draw this we'll use green here, dark green. So this state before only had edges to the two states above it, but now we're going to get an edge to this state right here. Okay, that'd be equivalent to moving the bottom with leaving the top. And then we also get a edge to the state right here, which also moves the bottom without moving the top. And so now what we could see, if the goal state is right here, where previously I had to make 1, 2, 3 moves to reach the goal, now I can make 1, 2 moves and reach the goal in 2 moves instead of 3. And this comes from, in a similar way that we did here, by taking one of the conditions on our operators and saying, let's relax that condition, and then let's see what happens. Okay, and so when we do that, what we've done is we've been able to connect together parts of the state space. And what we've got here is we're getting what's called an edge supergraph. And an edge supergraph is a graph that has exactly the same states or vertices or nodes, but the number of edges is strictly greater. So we take exactly a copy of the graph and we're going to add new edges to it. So in this case, of course, we did have two sets of graphs sitting here. They were disconnected. We added edges to them. So in some sense, we did make the graph bigger in the sense of what was reachable. And that's why we're going to maybe think about it from this example here, where I haven't changed the number of vertices at all, but what I have done is I've connected edges together. And then we're wanting to ask about this picture right here. Can I, with an edge supergraph, do this approach where I'm going to get this abstract problem that comes from an edge supergraph. I'm going to solve the abstract problem. Now, actually, what I didn't say here is here I drew it as going from the start to the goal. Typically, what I would do is from the goal, search backwards to the start. And then when I was searching down here, I would have this as guidance to get towards the goal down here. And okay, so what's going to happen here? Well, I've got this edge supergraph that I've built by relaxing my operators. And the question is this approach going to work? Is this approach going to be effective where I build the heuristic in the abstract state space and then use it to help down below? Okay, so an edge supergraph is, so we're going to say, just to say here, we're going to say T is an edge supergraph of S. So T is going to be equal to a set of vertices of T and edges of T. And S is going to be a set of vertices S and edges S. So T is an edge supergraph of S if the vertices of T is equal to the vertices of S, and the edges of S are a subset of the edges of T. Okay. And so this is the definition, just the formal definition of an edge supergraph. And what we want to ask the question is can we build a heuristic in an edge supergraph and use it to basically improve the performance of a search in a regular graph? And the answer to this question is no. So there's an edge supergraph, and this comes from something called Valtorta's theorem. Okay, so what does Valtorta's theorem say? Valtorta's theorem says if T is an edge supergraph of S, and and distances in T are computed with a breadth first search. Okay, so T's edge supergraph, we're going to do a breadth first search there. And then A star with distances in T are used as a heuristic for problem P. Problem P. Let's see. Then what we're going to find out. Okay, so what is the result of the theorem? It says for any S in, and so S is going to be a subset of the vertices in S. Okay, so this is in the original graph S that is necessarily expanded. Okay. If a breadth first search is used to solve P, then this is the key. Either S is expanded by A star in S, or S is expanded by a breadth first search in T. Okay, so what is this saying? It's saying, look, I've got T. T is going to be my abstract state space. So up here, this is T. I get rid of all the obstacles. And this is my edge supergraph of my original state space. Okay, so I've got this edge supergraph. I'm going to go in that, and I'm going to do a breadth first search to try and get some heuristic information. And then I'm going to use A star with distances in T as my heuristic for some problem P. And what I'm going to say is, look, suppose I don't have any heuristic at all. So for any state that's necessarily expanded, if I didn't have my heuristic, so if I didn't go build the heuristic in T, what I'm going to see is that either that state is going to be expanded by the A star, or it's going to be expanded by the breadth first search. But what it's saying is, no matter what, if S is necessarily expanded in the original problem with no heuristic, then S is also going to be necessarily expanded in my edge supergraph. And another way of looking at this or thinking about this is that when I get an edge supergraph, like if you look at here, I haven't reduced the size of the state space at all. Now I've added edges in here to connect states together and make it easier to solve the problem, at least in the abstract problem, but I haven't made the state space any smaller. And so it's no easier actually to solve, in some sense, it's no easier to solve the problem. There's just as many states there. And the idea is any work that I do to build a heuristic, will not be able to prevent me from doing work that I have to do to solve the problem optimally. It may prevent me from doing the same work that I did, like maybe I'm going to come here and say, well, this state, maybe I'm going to show that I don't have to look at it when I do my A-star search, because I'll get that heuristic information from the abstract solution. But basically it says, in some sense, with an edge abstraction, there's no free lunch, because I've either got to solve, going back to this picture, I either have to expand any states here or here. And there's no way that I'm going to get a savings. There's no state I can say, oh yes, I would have expanded it if I didn't build my heuristic. Like, maybe I would have expanded it here, and somehow I get some information that says I don't have to expand it in my abstract state space, and I don't have to expand it down here. That just simply can't happen. And as I said, that's part of the property of having an edge supergraph. And so Valtorta's theorem then seems a little bit depressing, because it says that there's not much that we can do. But it ends up that there is a solution to this. And what we're going to do is just assume this. So assume that we have some function phi, which is a surjective mapping between states. Okay, so what that is it's going to take, if I imagine I've got a bunch of states here, and what I'm going to do, surjective means it's going to be many to one. It could be one to one, but it's never going to be one to many. So the idea here is I'm going to take some set of states that were multiple states over here, and I'm going to represent them as a single state when I apply this abstraction. And so this is a key idea, is if I have some sort of surjective mapping, some sort of abstraction, then this is a different type of abstraction than building an edge supergraph. And it ends up that if we have an abstraction like this, that's a surjective mapping, we can actually get something akin to Valtorta's theorem. But because I can take multiple states and map them onto a single state in this abstraction, when I expand a single state over here, which would be a single, like if I think about S, when I expand a single state over here, it can actually save multiple expansions. So if this is just to be clear, like this is my abstract graph T, this is my original graph S. Now, if I have some sort of surjective abstraction, I can expand one state over here, and by doing one state over there, I might be able to avoid expanding multiple states over here. So what that's going to give us is it's going to give us a new it's going to give us a generalized Valtorta's theorem. And what this is going to give us is it's essentially going to give us a way forward. And in the next lecture, we're going to see how we can use this idea of generalized Valtorta's theorem to be able to do something efficiently. Let me just say one more thing I did forget to say here. So notice that this is all where we do this computation online. All the distances are computed online. It is possible that we could do an offline search, and we could amortize the offline search and reuse that search many times. It's also possible we could do some other kind of decomposition of our problem, and both of these might allow us to get savings here. But Valtorta's theorem is particularly saying, if we're going to do it with this process of a breadth first search and then A star versus just a straight breadth first search. Okay, and so generalized Valtorta's theorem is just going to say this: so T now is going to become phi of S, and I'll be very careful here. Phi of S, this is abstracting the entire state space. Okay, is an abstraction of S, the entire state space. And again, I'm assuming phi is a surjective mapping between states. Then we're going to say for any, and this is basically the exact same thing we have before. So for any, I'll write it a little bit shorter this time. So S in S, that is necessarily expanded using a BFS on problem P. then if A star is used to solve P using distances in phi of S, so our abstract state space computed by breadth first search, then either S is expanded by A star in S, or phi of S is expanded by our breadth first search in phi of the entire state space. Okay, and so the key idea here is that in this abstraction, our abstraction, we might abstract many, many, many states together. And therefore, I expand one state and potentially avoid expanding many states in my actual state space. Now, this may seem really abstract, but here, this is the general idea, is if I can come up a way with abstracting states together, then when I want to build a heuristic from that abstract state space, I will be able to have one expansion in the abstract space, avoid potentially many expansions in the low-level space. And in the next video, we'll look at how this actually works in practice and how we're able to build pattern databases out of this. So we're going to stop here and go ahead and look at the next lecture to see what's going on from here.